We will take few questions from this book. This is Engineering Mathematics, and this book is particularly very good for electronics, electrical, and communication and system engineers, people who are pursuing these branches of engineering. I have been doing questions from Erwin Krasnick's, which actually has also a lot of question on engineering mathematics, but that book is a kind of there you find question from mechanical engineering as well as civil engineering branches. But this one is totally focused on these branches. You won't find much of questions on piping or subjects related like thermodynamics and all. And we will actually do a question on ordinary differential equation from exercise number 19.3. Okay. We will do these exercises from question from 1 to 6, all of it, and all sub part of it we will be doing in this video. So without any ado, let us just start doing questions. Okay. First question I take is actually dy oblique dx is equal to 3. It says when the function y is differentiated with respect to x, we get a constant 3. Okay, and here actually from the question we assume that y is actually will be a function of x. Okay. What we can do in order to integrate or apply integral transform, we can actually do a variable separable process, and we will write this as dy is equal to 3 dx, and then apply integral sign on both the sides. So here it will be integral of dy, and here it will be integral of 3 dx. This will give us, here we will get y, and this side we will get 3 of integral x, which will nothing but 3 of x plus a constant of integration c. Putting constant of integration in this kind of problem is absolutely mandatory. If we don't put constant of integration, actually our solution will be incorrect. So you have to take care while writing an examination that you always put constant of integration if there is no initial conditions given. If there are initial conditions given, or if you are going to solve an integral which has a bound, then you might not be required to put a constant of integration. But otherwise, it is absolutely mandatory to put constant of integration in case you want your answer to be marked right. Okay. This is question A. Question B is also quite simple. This dx oblique dt is equal to 5. It says that actually x is a function of t and x is differentiated with respect to t. We can write dx is equal to 5 dt and then apply integration on both the sides. So we get here 5 dt like this, and x is equal to 5t plus a constant of integration c. This will be the answer. Now we come to question C, and question C is dy oblique dx is equal to 2x. There has been a change little bit from the earlier two questions, and the change is the first differentiation of y with respect to x actually produces a variable of x and not a constant. Okay, so we need to apply a formula in this, and by writing dy is equal to 2x dx, we know when x to the power n is differentiated with respect to x, our resultant or the answer we get is n x to the power n minus 1. In a similar way, when we integrate xn with respect to x, just the reversal of this, we will get x to the power n plus 1 divided by n plus 1. Okay, so these are the two formula which can be applied. Now we have already applied variable separable in this and separated y with y and x with x, and we can now apply delta y. This is integration sign on both the sides to get, and here we will get y. Since this is a constant, it remains actually inert to the entire process, and we can take 2 out of it and write x dx. If we compare this with this one, n for us here is actually n is equal to 1. So our answer will be what? It will be 2, then x 1 plus 1 on the numerator and 1 plus 1 in the denominator plus a constant of integration c. This will give us 2 is to x to the power 2 and 2 in the denominator plus c. This will go off and we will get x square plus c. So our actually solution for above will be y is equal to x square plus c. Exactly similar is question D. Question D is dy oblique dt is equal to 6t. I will not spend much time on this. Simply write dy is equal to 6 dt, apply integration on both the sides to get y is equal to 6t square divided by 2 plus c, or 3t square plus c. This is the answer. Then we have E. E is dy oblique dx is equal to 8x square. Separate as per the variable, and we can write dy is equal to x square, 8x square dx, okay, and we can apply this formula xn plus 1 n plus 1 here. In this case n is actually 2. Applying integration on both the sides, this is x square dx will get us y is equal to 8 x to the power 3 oblique 3 plus a constant of integration c, and our answer will be y is equal to 8 oblique 3 x cube plus c. F is dx oblique dt is equal to 3t cube, or dx is equal to 3t cube dt. We can apply a sign of integration on both sides to integrate it, and we can get dx is equal to 3t cube dt, or x is equal to 3t to the power 4 oblique 4 plus a constant of integration c, and this will give us x is equal to 3 oblique 4 t to the power 4 plus c. This will be our answer for F. Now there is a small change from F to G, and let us see. Dy oblique dx and x square y. On the right hand side, now you can see that both x and y variables both are given, means variable and dependent variable both are given, and in order to actually resolve this, we have to apply the process of separation of variable, and if we multiply, cross multiply, or if we multiply the entire expression with y, and we get dy oblique dx is equal to y is to x square y x square, and then we again multiply the entire expression with dx, and we get dx is equal to x square dx. This will go, and we get y dy is equal to x square dx. Apply integration on both the sides. You remember the formula that we discussed, xn dx is equal to xn plus 1 n plus 1. Now this will apply on both the sides here, on left hand side and right hand side. On left hand side we will get y to the power 1 plus 1 divided by 1 plus 1, and on the right hand side we will get x 2 plus 1 divided by 2 plus 1 plus a constant of integration c. So we get y square oblique 2 is equal to x to the power 3 divided by 3 plus c. I think this would be the answer for this particular problem. And now we come to question number H. Here question number H is dx oblique dt is equal to t cube x squared. Apply variable separation method to get t cube dt. Apply integration on both the sides to get here x cube plus 3 is equal to plus a constant of integration c. Now I dx oblique dt is equal to e to the power t divided by x, cross multiply dt, apply integration sign x square plus 2 here, e to the power t plus a constant of integration sign c on the right hand side. Then we come to question number J, dy oblique dx e to the power oblique y square, again variable separable, multiply with this, so y square dy is equal to x. Apply integration sign here, y cube oblique 3 divided by e to the power minus 2 divided by minus 2 plus a constant of integration c, and this will become nothing but y oblique cube plus e to the power minus 2x, 2 is equal to c. Okay, this will be the answer, friends. So we come to question number K, dy dx is equal to 6 sin x. Y, again cross multiplying like this, we get y dy is equal to 6. We can apply integration easily because these are variable separable equations, beautifully separated on either side of the equal to sign, and so we have y square divided by 2 is equal to 6 integration sin x dx, and we know differentiation of cos x is equal to minus sin x, and integration of sin x dx is actually minus cos x. So we can write here y square divided by 2 is equal to minus 6. Let it be plus, and sin x will be actually minus of cos x, we have multiplied plus a constant of integration c. And this will give us y square divided by 2 minus 6 cos x plus c. We can write y square divided by 2 is equal to c minus 6. KL. L is dx oblique dt is equal to 9 cos 4t divided by x square dx is equal to 9 cos 4t divided by multiplied by dt. This can be written as this. Now x is clubbed with x and t is clubbed with t, so we will have easiness. We will have actually ease in integrating these two equations. So we can write here. So this will become x to the power cube plus 3 equal to 9, and we have cos 4 theta. So let us integrate cos 4 theta d theta, and integration of cos 4 theta will become sin theta divided by 4. So 9 oblique 4 sin 4 theta plus a constant of integration c. Okay, so therefore x cube divided by 3 is equal to 9 oblique 4 sin 4t plus. So friends, we will discuss question number M now. This is little tricky and we need to be careful. Cos 2t on the denominator of the numerator on the right side, and then 8 sin 4t plus x squared plus x. Now separating the variable, we can get actually x square plus x dx is equal to 3 cos 2t plus 8 sin 4t dt, or x square dx plus x dx is equal to 3 cos 2t dt plus 8 sin 4t dt. Now the moment we apply integral operator on both the sides, it will apply to each element of it. So we will have x squared dx plus here, x dx here. This will be 3 cos 2t dt plus 8 sin 4t dt. As per the formula, we will get here x cube oblique 3, x square oblique 2 is equal to 3. Cos will be sine, so this will be sine 2t divided by 2 plus sine will be minus cos, so this will be 8 is to minus cos 4t divided by 4 is equal to 6. So, okay friends, so we move to the next section now. Next question is question number 2. It has also got a total 5 questions, but question 2 will be an initial value problem. So how do we calculate a constant c in initial value problem? We are going to see in the next section. Okay, kindly continue watching the video. So we now take question on of section 2 of 19.3, and section 2 questions are all initial value problems. These are also pretty simple when you did not do much work here. This is 3t, and we will get here 3t dt. Apply integration on both the sides to get x is equal to 3t square oblique 2 plus a constant of integration c. Now we have to find the constant c using the initial condition, which is given as x0 is equal to 1. And this actually says that the value of x is equal to 1 when the value of t is equal to 0. When t is equal to 0, x is equal to 1. We substitute this here, and at t is equal to 0, we substitute 3 oblique 2 is equal to 0 plus c, and then x will be 1 at this point. And this will give us nothing but, this will become 0, and this is on the opposite side of the equal to sign, and we get c is equal to 1 simple here. Okay. So now our next step will be to substitute this the value of c here to get our equation. So we get x is equal to 3 oblique 2 t square plus 1. And now you can see this particular equation is actually 3 of any unknown constant. The only constant is 1, which is known to us, and our answer will be 3 oblique 2 t square plus 1. Right friends, so we move to the next one. Again very simple. Let us make use of initial condition here, and at x is equal to 0, y is equal to 1. This will be 1 oblique 2 plus 2, 0 cube plus c, and this will give c is equal to half, and our answer will be y square 2 square plus 2x square plus half, or we can do a little bit of tinkering and we can also write it. I will multiply the entire expression with 2, and we will get y square is equal to 4x square plus 1. This could be our answer. This is not x square, but this is actually cube. So y square is equal to 4x cube plus 1 will be the answer. Now we move to c. C is y square divided by 2 This will become 3 integration of sine, and integration of sine gives us cos minus cos. So this will be minus 3 cos of t and plus c. Okay. Apply the initial condition t, we have to use 0, and y we need to substitute 2. We will substitute 2 square divided by 2 is equal to minus 3 of cos 0 plus c, and this will actually become 2 is equal to minus 3. Cos 0 is 1. We know that cos 0 is 1. So this will be minus 3 plus c. So here we'll get actually c is equal to 5, and this c we need to substitute here to get y square oblique 2 is equal to minus 3 of cos t plus 5, or 5 minus 3 of cosec t. And I think this will be the answer. Okay. Y square oblique 2 is equal to 5 minus 3 cos t. We move to the next one. Next one is actually involving an exponential function, and this is the, okay, so we can write it again, right? At x is equal to 0, y will be 3, it says. So y, then y square is 3 square will be 9. 9 oblique 2 is equal to minus of e to the power minus 0 will be nothing but e to the minus e to the power 0 plus c, and e to the power 0 will be 1. So this will be minus 1 plus c. C will be 9 plus 2. This minus will come this side and add here. So this will become plus 1. And this will become 11 oblique 2. Okay. So we need to substitute c here with 11 oblique 2. So we will get y square divided by 2 is equal to minus of e to the power minus x plus 11 oblique 2. And this will get us actually 2. If I multiply the entire expression with 2, we will get 2 here and 2 here and 2 here, and this will then become y square is equal to minus 2 of e to the power minus x plus 11, and this will give us y square is equal to 11 minus 2 e to the power minus x. And this is the answer for this. D is solved. Then we come to the last one, which is actually E. And the last one is dx oblique dt is equal to 4 sine t plus 6 cos of 2t divided by x. We apply integration here, and this will be actually 6 cos will give us a sine 2t, and then we will divide with the constant multiple of the variable, and it will be 2 here plus c. This will give us 3. This will be minus 4 cos 2t plus 3 sine of 2t. This will be 2 to the square of 2 is equal to minus 4 of cos 0 sine 0 plus c. So friends, we have come to question number 3. Question number 3, interestingly, just have this particular question, and this is a kind of little complicated compared to what we have solved, because we need to actually apply integration by parts process in this case. ln t dt. Okay. The moment we apply integration on both sides, we get. Now there is no formula to actually straight away formula which can actually give this integration on the right hand side. So what we do, we actually use integration by parts. There is a formula of integration by parts which is like u dv is equal to uv minus v du, and we do an assumption of what should we select u and v here, and we do an assumption of normally called ILATE. I is for inverse, which means if there is an inverse in the integration in this function, our priority to select that as a u should be 1. Then logarithm is actually 2, algebraic is 3, trigonometric is 4, and exponential is the last choice. We already have logarithm function in this particular thing. So we select u as ln t, and therefore dv will be actually nothing but 1, because it is actually anything which is written in isolation is always a multiple of 1. So this is also a multiple of 1. So we have u is equal to ln t and dv is equal to 1, and both of these will be integrated or differentiated with respect to the variable which is t. So if we write du, actually what we will get on the right hand side will be differentiation of ln t with respect to t is to dt, and this will be nothing but 1 oblique t dt here. And then for v we need to integrate this one, and the moment we integrate this particular thing, dv is equal to 1, we get v is equal to t. So we got here u and v. So 1 is to ln t dt, which is nothing but this here, is equal to uv, which is with no t here. No, there is no t here. U we take ln t here and v here. So we will have t ln t. Instead of writing uv, I have written in vu for avoiding confusion later on. So we will have t ln t here and minus of v is what? V is t, and then du is what? Du is 1 oblique t dt. This will cancel each other out, and on here we get only t ln t minus of integration of dt, and this will give us t ln t minus t plus a constant of integration c. Right, friends? So we have our solution now of this, and this is t ln t minus t plus c, or we can write x is equal to t ln t minus t plus c. Now we have to make use of the particular we have actually general solution for this as this one, x is equal to t ln t minus t, and since you know that logarithm for any negative function is not defined, so usually we write in a modulus, and then this will be minus t plus c. This is general solution. Particular solution will be when we actually find c using the initial conditions given. The initial condition given here is actually x 1 is equal to 1, which means at t is equal to 1, the value of x will also be 1. Here we write 1, and this will be 1 ln 1 minus 1 plus c. This will become 0 and c will become 1 plus 1, 2. Therefore, particular solution will be xt is equal to t ln of modulus t minus t plus 2. So this will be the answer. Now let us move to the fourth question. Fourth question also has got subparts now. Fourth question will start from A and it will be going till G. Okay. We will solve all of that. P is dy oblique dx. Here, if the C is constant, we have assumed we can substitute C with another constant ln A. It doesn't matter, it will be one and the same. Then we can bring ln A on the left hand side and write ln y minus ln A is equal to minus kx, and this will give ln y oblique A is equal to minus kx. And this will actually, when we take anti-log, we will get y oblique A is equal to e to the power kx, or y is equal to a e to the power minus kx. And this will be the general solution. Okay. Let us move to the next question, which is C. C is dy oblique dx is equal to y square, and this can be written as y square is equal to dx. Apply integration both sides. Left hand side will be 1 oblique y. Okay, I'll add few more steps. I'll take it y minus 2 dy is equal to dx, and we remember the formula of here n is equal to actually minus 2. Left hand side will be actually y minus 2 plus 1 divided by minus 2 plus 1 is equal to x plus c, and this will be y minus 1 divided by minus 1 is equal to x plus c, or minus 1 oblique y is equal to x plus c. Therefore, the general solution for this will be y is equal to minus of 1 divided by x plus c. We come to t, y dy oblique dx is equal to sine x, y dy is equal to sine x dx. We will choose to multiply the entire expression from LHS to RHS with d of x or delta of x to get this. Now apply integration. On the left hand side it will become y square oblique 2, and on the right hand side it will be minus cos x plus c, where cos x is actually a constant of integration, and we write y square is equal to minus of 2 cos x plus another constant we can assume, or we can write 2c. 2c is also a constant, so we can write c, or I will choose to write c1, and y is equal to c1 minus 2 cos of x square root. This will be the general solution for this one, or you can write this also as a general solution for this. Y, this will give y dy is equal to x plus 2 dx, integration y square oblique 2 divided by x square 2 plus 2x plus c, or y square is equal to x square plus 4x plus c1 and this will be the general solution. X square plus 4x plus c will be the is equal to y square will be the general solution. This one is a little tricky, and actually we will have to use Bernoulli's equation in this. Delta y oblique delta x plus px y is equal to qx. I think we need to form something like this in order to resolve this one. And I divide the entire expression with x square to get dy oblique dx here plus 2y square x square plus yx oblique x square, and delta y oblique delta x will be actually here it will be y oblique x plus 2 is equal to y square x square. We may not do this. We can also assume y is equal to vx, and then dy oblique dx here we will give v plus x dv oblique dx. We replace this here v x dv oblique dx, and here since we have assumed y is equal to vx, y oblique x is equal to v, we can replace this one at both places. On the right hand side we get v plus 2v square. This v will go up with this, and we will be left here x dv oblique dx is equal to 2v square. Okay, and now we can do a variable separable, but if it can be done beautifully, we have to take 2v square on the left hand side. This will go in the denominator here, so this will be dv 2v square here, and this will be dx here, and x will come in the denominator. Okay. Now apply integration on both sides here. Okay. This will be half integration of v to the power minus 2 dv is equal to x half v minus 2 plus 1 divided by minus 2 plus 1 ln x plus c. Half of minus of 1 oblique v is equal to ln x plus c. Now v is what? We had assumed here y oblique x, so we will replace y oblique x here, and we will get here minus of 1 of y oblique x will be x oblique y at this place, and ln x plus c will be at this place. So we take y this side and bring ln x plus c on the denominator of this, and our solution will be in this particular form here. This could be solution. In the book the answer is given little different, but it is actually one and the same. This can be written as they have actually removed negative sign, which is actually merged with the constant, and x oblique 2 ln x it is written here, and it is minus sign is here, and then minus 2c is there. Now minus 2c can be replaced with any other constant a, and the moment we write there, we will get x is equal to minus 2 ln x plus a, and this will become nothing but x divided by a minus 2 of ln modulus of x, and this is the answer. Okay, so we are left with just one question in this section, which is question number G. In question number G, we take dx oblique dt is equal to t to the power 4 x to the power 5. We can do variable separable by cross multiplication. X to the power 5 dx can be written as t to the power 5 dt. Integrate both sides, and we will get x to the power 6 is equal to t to the power 5 oblique 5 plus c. and actually this will be the general solution. Okay. So friends, so let us move to the next section, which is section 5, and we have to find, in that case also we have to find the general solution. Section 5a is dx oblique dt is equal to xt, and here also we will separate the variable in order to integrate it and apply integration here. Ln x will be t square oblique 2 plus c. C can be written as ln a, and we write ln x is equal to 2 square oblique 2 ln a, and we take it this side, okay, and ln a minus, sorry, ln x minus ln a is equal to t square oblique 2 ln x oblique a. Applying anti-log, we get x oblique a on the left hand side, and on the right hand side we get t square oblique 2. This will give us nothing but x is equal to a e to the power t square of 2. This is the answer. Okay. Fifth B is dy oblique dx, x oblique x oblique y, cross multiply like this, y dy is equal to x dx, and this will y square 2 is s square 2 plus c, and this can be written as y square is equal to x square plus a, where a is the constant of integration. It is one and the same. You could also write c, or whatever constant you want to write, it will be correct. Now c is t dx dt is equal to tan x, and separating the variable we will have 1 oblique tan x dx is equal to dt oblique t, 1 oblique tan x is equal to cos x dx sin x dt oblique t, and if we assume on the left hand side sin x is equal to p, the differentiation of this will actually be cos x dx is equal to dp. So we can actually write dp oblique p here and dt oblique t here, and both of it when integrated will give ln p is equal to ln t plus ln a. Or we can write p is equal to a t, where a is actually nothing but constant of integration, and ln a is also a constant of integration. And p we had assumed what? Sin x. So we will have actually sin x is equal to at, or x is equal to sin inverse of at, you can write. Now a is any constant. You can denote it by any alphabet you choose, a small cap, lower cap, whatever you choose, you can do that. Now come to question number D. Question D is actually dx oblique. Now apply integration here. We can actually use formula which is given on for x square minus 1. This is nothing but if I write this will be x minus x plus 2 half, okay, and integration t, and this is nothing but log of x minus 1 minus x plus 1 is equal to 2 log of t plus log of a, or log of a t square plus log of t square plus log of a, or log of t square at square, and this is log of x minus 1 divided by x plus 1. We take antilog on both the sides and simply we will get x minus 1 divided by x plus 1 at square, or x minus 1 is equal to x at square plus at square, and we take x this side, we get x 1 minus at square, and we take 1 this side, it will come and add here, and it will become 1 plus at square. Therefore, the general solution of x will be actually 1 plus at square divided by 1 minus at square. This will be the solution. So friends, so we are on the last question now of question section 19.3, and last question is 6. 6 is again a single question with no subpart, and it says we have to find general solution and particular solution of an equation. Dx of the dt is given, and we have to write it is given like this, and we have to find general solution of this and particular solution when x0 is equal to 5. So dx x minus 2 is equal to t dt, and apply integration here, we get ln x minus 2 modulus t square of the 2 plus I write a constant ln a. I take ln a on this side to write x minus 2 of the a modulus t square of the 2, and then apply antilog to get x minus 2 divided by a is equal to t square of the 2, and then a is cross multiplied with exponential t square 2, so we have x minus 2 a e to the power, or x is equal to 2 plus a e to the power t square of the 2. So this becomes actually general solution. Now particular solution we have to find when t is equal to 0 and x is equal to 5. So we can write 5 is equal to 2 plus a e to the power 0, or 5 is equal to 2a. This gives a is equal to 3, and when we substitute we get x is equal to 2 plus 3 e to the power t square of the 2. This is PI, particular solution. Okay. Right friends, so we are done with section 19.3 of engineering mathematics by Antony Croft, and all question has been solved in this particular video. Once again, before I leave, I would like to request, if you have liked my video, you are requested to subscribe to the channel. Click on the like button of the video and share this video widely with your friends. Okay, and you can also request them to subscribe to the channel. I will be back again with another set of questions, either from classic mathematics or from this Croft's engineering mathematics very soon. Thanks a lot for joining in Maths Maestro. Bye bye.